Hi there, folks. In this lesson, we're looking at properties of rhombuses, rectangles, and squares. And as you read down through these definitions, there's a common theme here that's really important, and it's the fact that each of these things is really a parallelogram. So, like when you look at a rhombus, it's defined as a parallelogram with four congruent sides. A rectangle is a parallelogram with four right angles. And a square is a parallelogram with four congruent sides and four right angles, okay? So the fact that all of these are parallelograms is really important because if they're parallelograms, they have all the properties of parallelograms. So all the things we know about parallelograms still apply to every single one of these things. But now we're going to have some special properties for each one because of the special conditions that they have, okay? So a rhombus is a parallelogram, four congruent sides. Another way to say that would be to say that a rhombus is equilateral. Remember, equilateral shapes, all the sides are congruent, and that's the case with the rhombus. So it's the special parallelogram that's equilateral. Rectangular is a parallelogram with four right angles. So if all four angles are right angles, it means all four angles are congruent. So this is the special case of a parallelogram that's equiangular. And remember, that's another special term that we had for any polygon where all of the angles are congruent. And then the square is a parallelogram with four congruent sides and four right angles. In other words, it's equilateral and equiangular, and we had a special name for that as well. And remember, that just means it's a regular polygon. Remember, regular polygons are polygons that are equilateral and equiangular. They're basically like the perfect version of that shape. So when you think about a parallelogram, it's a quadrilateral. Okay, so it's a special kind of quadrilateral where the both pairs of opposite sides are parallel. And then a rhombus is that same thing, but with all the sides congruent. A rectangle is that same thing with all the angles congruent. And a square is that same thing with all of that stuff congruent. Okay, so it's the opposite side, or all of the sides are congruent, all the angles are congruent. Okay, and so that makes it a little bit tricky when you start classifying these things, because when you think about it, a square is a rhombus and a rectangle. See, because it meets all those criteria, but it's also a parallelogram. It meets that criteria as well. So when you see something that's a square, you can classify it as a parallelogram, a rhombus, a rectangle, and a square. All right, so it's important to kind of work through this progression of, okay, is it a parallelogram? Is it a rhombus? Is it a rectangle? Is it a square? And list all that apply. For example, if I look at something like this, I want to classify each. So again, I'm going to start with the most basic. All right. It already tells me it's a quadrilateral, so I don't need to write that one down. So I start with the basic one that I have, and is this thing a parallelogram? And so when we look at this first one, you see that the opposite sides are parallel to one another. So since the opposite sides are parallel, I know that this thing is a parallelogram, so I write down parallelogram. And then I look for whether it's a rhombus or rectangle, so I look for rhombus. And so here's the thing. You notice right here that I've got this side congruent to this side. But since I already know that this thing is a parallelogram, I know that opposite sides are congruent, so that means this side is equal to the side across from it. And it also means that this side down here is equal to the side across from it. And so now as I look around this thing, each of these has one dash, which means all of the sides are congruent, so this one's a rhombus. And then from there I look at the angles. If I can conclude that all the angles are right angles, then I conclude this thing is a rectangle, but I can't on this one. All right, so I move on to the next one. So again, the next one, I start with the looking to see if this thing is a parallelogram. And once again, I see that opposite sides are parallel, so I know it's a parallelogram. That's the definition of a parallelogram. And then I look to see if all the sides are congruent, and there's nothing that indicates here that all the sides are congruent, so I can't say that. So then I look to see if all of these are right angles, and again, since I know this is a parallelogram, I know that opposite angles are congruent. That's these guys. I also know that consecutive angles are supplementary, and here's the thing. If these two angles are supplementary, and this is a 90-degree angle, this one also has to be a 90-degree angle. And then I could do that same thing to find the last angle. Or I could say that all the angles have to add up to 360, so this has to be 90. Or I could say that opposite angles are congruent and say that that's also 90 degrees. So now I have all the angles are congruent, all the angles are right angles, so this one's a rectangle. And then this last one, once again, I see that opposite sides are parallel, so it's a parallelogram. I notice that two of these sides, these two right here, this one and this one, are listed as congruent, but since it's a parallelogram, opposite sides are congruent as well, so this side has to be equal to the side across from it. This side has to be equal from the side across from it. So now I can see that all of the sides are congruent, so it's a rhombus. I notice a right angle there, and I know that the opposite angle has to be congruent, so that's a right angle. These angles are supplementary, consecutive angles are supplementary, so that one has to be a right angle. And then this last one also has to be a right angle. And I can figure that out through consecutive angles or opposite angles being congruent or what have you. And so as soon as I see that all of these are right angles, I can declare that this thing is a rectangle. And now this is basically the definition of a square, is that it's a rhombus and a rectangle at the same time. So as soon as I see these two classifications of rhombus and rectangle, I can immediately then conclude that this thing is a square. Okay, and so please keep that in mind. Squares are really special because they are parallelograms, they're rhombuses, they're rectangles, and they have that special classification of a square. Okay, but as soon as we see rhombus and rectangle on the list, square is automatically on the list. Okay. In this one, we want to prove that basically that the diagonals of the rhombus are perpendicular to one another. So I'm given that I have a parallelogram ABCD is a rhombus, and I want to prove that BD and AC are perpendicular, so the diagonals are perpendicular. Okay, so I'm going to throw out some statements and some reasons here. And I'm going to start with the given. That's what I always start with. And keep in mind, once again, there are a bunch of different ways that we can do this proof. I'm just going to pick the first one that pops into my mind here. Normally I would ask for your input, but that's a little tough since I'm all by myself right now. So here's the route I would probably go. First of all, knowing that this thing is a rhombus, I know that all the sides are congruent. So I'd probably start with something like AB is congruent to BC. Okay, and really I could say AB is congruent to BC, congruent to CD, congruent to AD. I could do all of those, but frankly I don't think I need that. Keep in mind that just knowing it's a parallelogram, I know that the opposite sides AB and CD are congruent. So what's really kind of special when you whittle it down is the consecutive sides being congruent. So I just labeled one of those pairs. I can go back and label more of these pairs later if I need to, but I think that's all I'm going to need. And that's just the definition of a rhombus. From here, I could say something like AE is congruent to EC. And I know that because even though this is a rhombus, it's still a parallelogram. Rhombuses are automatically parallelograms, so all my rules for parallelograms still exist. Well, I know in a parallelogram that the diagonals bisect each other. So if I have a parallelogram, then the diagonals bisect each other. Okay? And then I also know, see in step 4 here, that BE is congruent to itself. And that's just my reflexive property. And now what I've established here is really two triangles where all of their sides are congruent. So triangle AB is congruent to triangle CBE. Oops, I forgot my triangle symbol. And really that's simply through side, side, side. Okay, now that I know these two pieces or these two triangles are congruent, I'm going to label some angles here. I'm going to call this angle 1 and angle 2, just to save myself a little bit of work so I don't have to say angle AEB and angle BEC. I'll just call them angles 1 and 2. And so now I can say that angles 1 and 2, angle 1 is congruent to angle 2, and that's because of CPCTC. If I know that angles 1 and 2 are congruent, those are obviously a linear pair, and so if I have congruent angles that form a linear pair, two angles that are supplementary, that are congruent, they have to be right angles, okay? So now I can say that angles 1 and 2 are right angles. And again, that's a kind of a theorem we had, but if, I believe it was the congruent supplements theorem, if supplementary angles are congruent, then we have right angles. Okay? And so now I'm pretty much done here. I just have to do the proof statement. Now I know that BD is perpendicular to AC, and that's just the definition of perpendicular lines, is that two lines that form a right angle, and I've established that they're right angles in the previous step. Definition of perpendicular. Okay? And so this unique property that we have basically says this: if we have a rhombus, if you're dealing with a rhombus, then the diagonals are perpendicular. Okay, and that doesn't change the fact that the diagonals bisect each other. This thing's still a parallelogram, so yeah, the diagonals still bisect each other. But now, what's special about a rhombus is that they're also perpendicular to one another. Okay. We have another theorem about these, and really, it's basically the same proof. We go through the same steps of the proof, and then just using CPCTC, we could show this theorem, and so that's why we're not going to actually do this proof. But again, if it's a rhombus, not only do the diagonals bisect each other, and not only are they perpendicular, but this last one is that the diagonals bisect each pair of opposite angles. And so when we look at the diagram, when we look at the angles over here, those are congruent. They're being bisected by that diagonal. Same thing over here. They're being bisected by that diagonal. These are being bisected. These are being bisected. Okay? And so that's what this theorem is establishing. And really, if you think about the proof we just did, you know that you can show that all the triangles in here are congruent, the same way we just did the previous proof. And then CPCTC would give us all of these. It would give us that angle 1 is congruent to angle 2. But then those are also congruent to this other set of angle 6 and angle 5, which are also congruent. Again, those diagonals are bisecting those opposite angles, and that's why those little angles are congruent. Same thing with these other guys. I've got angle 3 is congruent to angle 4, and those are also congruent to the set of angle 7 and angle 8 being congruent. Okay? And so if we kind of use this looking at a couple rhombuses here, and for these examples we're going to assume that these are rhombuses. And so if I assume this is a rhombus, if I look at this thing and I start saying, okay, let's find the measurement of each angle, I know that the measure of angle 1 has to be 90 degrees. That has to be a right angle because the diagonals in a rhombus are perpendicular. The fact that this guy up here is 52 degrees, well, remember that matches this set of angles, and those are congruent, so that means that the measure of angle 2 is also 52 degrees. The measure of angle 3 is also 52 degrees. And now the only one that might be maybe a little bit tricky here is angle 4, but keep in mind, I've got 3 angles inside a triangle here. I know that this one's 90, I know that this one down here, if I label it as 52 degrees, and I know that the 3 angles inside a triangle have to add up to 180, so the measure of angle 4 has to be 38 degrees. Okay, because that whole triangle has to add up to 180. Okay. Same thing when I kind of look at this guy. I know that this thing is a rhombus. We're assuming that for these examples, and so I know that the opposite angles bisect each other, and so it's important to understand that these guys are congruent to one another. Okay, so those pairs are the same as well, and then these guys are congruent, and then this guy is congruent. So all four of these angles are congruent, and so when I look at just specifically this bottom triangle down here, I've got a 102-degree angle. The other two angles have to be the same, and they all have to add up to 180. Okay, so each of those angles has to be 49 degrees, it looks like. Or no, sorry, 49 degrees. Sorry, they have to add up to 78 degrees. So they have to be 39 degrees. Oh my. So the measure of angle 1 has to be 39 degrees. The measure of angle 2 has to be 39 degrees. The measure of angle 3 has to be 39 degrees. And the measure of angle 4 has to be 39 degrees. Okay? And it's basically like we're dealing with an isosceles triangle. The base angles are congruent. So 1 and 3 have to add up to that 78 to give me the 180, and that's why they each have to be 39. And then 2 and 4 just kind of follow suit because they're all going to be the same. Okay? For this one, we're given that ABCD is a rectangle, and so now I know this thing is a rectangle, and I want to prove that the diagonals are congruent this time. Okay, so this is going to be one of my special properties for the rectangles, that the diagonals are congruent to one another. Again, all of the things that we know about parallelograms are still true here, like opposite sides being congruent, the diagonals bisecting each other. We can't apply the rhombus rules. We can't say that the diagonals are perpendicular because that's only for a rhombus, and a rectangle is not necessarily a rhombus. Okay, so let's start our proof. Let's do some statements and some reasons here. And of course, I always start with what's given. So parallelogram ABCD is a rectangle, and that's given. And then from here, really, as we start to think about this thing, almost everything we've done has been through the route of getting congruent triangles in this thing. And so that's kind of what I'm going to do here, and I'm going to kind of focus on two of these big triangles, like this guy and, well, let me use a different color, and this guy right here. I'm going to try to establish maybe those two triangles, because then through CPCTC I'd have the diagonals congruent, okay? So I'm going to start with that. So I'm going to go this route and say that AD is congruent to BC. And that's because the opposite sides of a parallelogram are congruent. So maybe I'll do it as an if-then statement, since that's how. So if I have a parallelogram, then the opposite sides are congruent. Okay. I also know that it's a rectangle, and there's really no way around how I'm going to label this, but now I can say that angle ADC and angle BCD are right angles, and that's because they're just the definition of a rectangle. And now once I know that those two are both right angles, I can immediately say that they're congruent. And that's because all right angles are congruent. I can also say that CD is congruent to itself. And that's the reflexive property. And now if you're paying attention to what we have here, and it might be helpful if you draw these two triangles separately, what I have is these opposite sides are congruent. I have that this guy's congruent to itself, and I have the angle in between. Sorry about that. And I have that the angle in between are congruent. So really I have side angle side here. So I can say that the two triangles in question, triangle ADC, is congruent to triangle BCD, and that's because of side angle side. And now I can say that those two pieces are congruent. So BD is congruent to AC, and that's because of CPCTC. Okay? And so, again, this is our special property for rectangles, is that the diagonals are congruent to one another. So again, the same rules for parallelograms still apply. So in a rectangle, the diagonals still bisect each other, but the diagonals are also congruent now. All right, and that's really important. And so if we apply some of this, we'll look at something like this guy. It says in rectangle ABCD, AC is 4x minus 17, and BD is 2x plus 13. And then I want to find the measure of DE. Well, right away, it's listing the diagonals for me. Since I know that this is a rectangle, I can just say that the diagonals are equal to one another. That's one of the special properties. And now I can solve this thing. I'll subtract the 2x. I'll add the 17. And now I'll divide each side by the 2, so I get a 15. But then it asks for DE, okay? And so what I have to do is I have to plug this back in. Maybe I'll look at the measure of BD. If I look at the measure of BD, if I go ahead and I plug that 15 back in for BD, I get a 30 plus 13. Well, maybe I'll just show it. I'm plugging the 15 in here. So it's 30 plus 13, which is 43. Well, that's the length of BD, but I still know that this thing is a parallelogram, which means the diagonals bisect each other. So DE has to be half of that, so it's going to be 21.5. Okay? And so again, just because it's a rectangle doesn't mean it loses those properties of the parallelogram. It still has all those, but in addition to that, it's got the special property of the diagonals being congruent. Okay? And so here's the thing I want to ask about a square. Okay? And you have to understand that a square is a parallelogram, a rectangle, and a rhombus all at the same time. So if I ask you about the diagonals of this square, first and foremost, you know that the diagonals bisect each other. And you know that they bisect each other because this thing's a parallelogram, and that's the property we had for the diagonals of parallelogram. Okay? We also know that they're perpendicular to each other. And you know that they're perpendicular to each other because a square is a rhombus, so it adopts the properties of a rhombus. You also know that they bisect the opposite angles. And again, you know that because that's a property of a rhombus, and a rectangle is a rhombus. It takes on all those characteristics. And then lastly, you know that the diagonals are congruent to each other. And that's because a square is a rectangle, so it adopts all the properties of a rectangle. Okay? So again, we still have all the properties for a parallelogram. The rhombus has some additional properties of the diagonals being perpendicular and bisecting the opposite angles. And then for a rectangle, we have an extra property on top of the parallelogram properties that the diagonals are congruent. And so with a square is a parallelogram, a rhombus, and a rectangle, so it has all of those special properties. Okay?